Evertson. Oh, I got worried when I got that message. Okay, thank you. Today, I'm really pleased to present our colleague here at Chalmers University of Technology, Dr. Kanishk Bhadani. Kanishk is a very enthusiastic researcher and extremely productive, I would say. He got his master in product development here at Chalmers in 2016, if I'm right. He started to work for our group for about a year in different projects related to crushing and screening and aggregates production. And then between 2017 and 22, which is the normal 5-year period for a Swedish PhD, he worked on his PhD and he got the grade last year. So Kanishk took on a task that I actually thought was impossible, because I know the complexity of simulations. And when we do dynamic simulations, you get even more higher complexity compared to stationary, because you have to model the control system as well. And then to add an optimization on top of that, that was tempting, I have to say, but I was quite worried that this would be too much. It wouldn't be possible. Kanishk has shown the opposite in a very good way. And as I said, he was appointed his doctorate degree last year. And since then, he's been employed here at our group, at Chalmers Rock Processing, as a postdoc researcher. So I guess there is a lot more to say. As I said, this is quite a deep type of research, very complex. And Kanishk has also done a lot of site surveys. So both in Swedish aggregate quarries in Europe, and also at some of the major gold producers that you would know about. So with that, I'm happy to introduce and leave the floor to you, Kanishk. The floor is yours.
Thank you, Magnus, for the nice introduction. And welcome everyone for this seminar, where I will talk about, basically I will go through some of the developments which we have been doing in the past 5 years regarding optimization capabilities for crushing plants, and how we see it and how we define it and what is needed to take things forward. So as Magnus introduced me already, I'm Kanishk Bhadani. I'm a postdoc researcher at Chalmers Rock Processing Systems, and my focus has been within the development of optimization methods, and mostly to implementation, finding the right implementation within this industry. And I'm also currently involved within a European project, Rotate, which is about developing environmental platform on top of process simulation. So let me put you a little bit of a background about what I mean by optimization capabilities as a scope, where I'm heading, or putting a layer out what I will be talking about. So most of the physical plant, if you just think about a crushing, where I'm just now talking about cone crushers, jaw crushers, and vibratory screen, the dry processing in minerals and in aggregates is there. It's where the products comes out at different size fraction. You can think about, there are two parts where is design, when you are actually building a plant, new plant, and when you're operating a plant. And when you are at these 2 points, you are having a lot of data. And this data could be, what kind of material are you processing within your circuit? What kind of equipments do you have in your circuits? And what kind of process layouts do you have in your circuit? And with that data, when you have a process layout with the SCADA and PI system, you can also get the different productions happening, different control signals. So you have a lot of data which exist within the circuit and within the production process. Also, as a researcher, we could also extract data by doing a controlled experiments at these sites. So when you have this abundance of data, where you want to take it, one of the usage is that we want to create a reliable process and equipment models and simulation. And to fit this data into a process simulation models, we need optimization functions. And that is basically meaning we need some sort of error minimization problems using optimization to fit these data closer to the, fit these models closer to the data. And then once we have these reliable process models and equipment models, then what do we do with that then? Most likely we'll try to put or calculate some kind of KPIs, key performance indicators. It could be anything. You want to maximize your throughput or maybe product yield. It could be anything, any sorts of KPIs within that. And then based on that, then you can say, okay, now I need to improve, do some sort of improvements, and maybe that will result into a new sets of optimization problem, which you can then do it on the simulation models. And in order to extract more knowledge out of these simulation models, we need another sort of optimization functions on top of this, which can help us to generate design and operational knowledge, which then we can feed back into the physical plant design and operation. So what I'm going to talk about is mostly what optimization looks like at this level and what optimization could look like at this level. So in my thesis, I presented a translation to digital twin model, that how could we connect our physical process into simulation system. So for every operation, there could be a parallel process and equipment model. It already exists, many of the models. And once we go into the second level, where we have a lot of data online and offline, then we can talk about some implementation where we need to make sure that these data are used by this simulation models and they are continuously in communication. And on top of these two, we can then do a KPIs. And if you do think of from a physical system, you want to increase your performance control. But from a simulation point of view, we are trying to increase the simulation utilization by adding more functions to the simulation platforms. And then if you have on top optimization function where you can learn about a lot of possibilities within these systems, then you can transfer that knowledge back into the process operation or design. So I will specifically show you 3 examples today: process simulation, equipment model calibration and validation, a little bit of a detailed work which we have done within the group. Second, I will also show you the KPIs, how we could model the KPIs within the simulation system and also on the physical systems. And a lot of companies already have this, but it's just to enable the capabilities within the dynamic simulation. We have worked with that. And then last one is that how could we achieve some optimization application and practical implementation on a larger scale on top of this simulation. So before I go into details of these application, I would spend 5 minutes to just give you a little bit of an overview of what is optimization, because we hear this word a lot in many research paper titles and many projects. Everything starts with optimization. So let me give you a little bit of a brief what it contains from my experience, or what from mathematics point of view. So it's a very famous book which is used in aerospace and automotive industry, is Principles of Optimal Design, and Professor Papalambros has defined it as an optimization of a system as a decision-making process of choosing the best alternative which meets the original needs within the available means. So it's a decision-making process of choosing the best solution, meeting your needs and your available means. So what does it mean for design and operation of a crushing plant, the definition? So I did a translation of that and a little bit adopted this definition. So for a crushing plant in operation, optimization capabilities can be defined as the process of choosing best operational settings for a given circuit configuration, means your layout is fixed, to meet the performance needs of the stakeholders. And I say performance need of the stakeholder because if you're a sales or if you are on a production, these performance needs, the KPIs will differ. And for a crushing plant in design, if you're building a completely new design, optimization capabilities can be defined as the process of exploring or selecting the best design solutions for a given circuit requirement. So you are posed with a certain requirements within the circuit to meet the performance need of this stakeholder. So here you are trying to select the best operational settings with your given resources. And here you're trying to design the best solution that could give you the requirements. So these are just definition, but I will go a little bit on details. So in order to do an optimization mathematically, we need some form of mathematical models and relationships, or basically in our case, it's a simulation system or models, where we can input certain variables and parameters and we can extract certain outputs. And it's basically, I call this as a system function. So mathematically, optimizations are as a negative null form is defined as I presented. So it's basically, it contains a few different things. So first is objectives. What do you want to minimize? And usually in mathematics, we talk about minimizing a function. But if you want to maximize something, you just either reverse the function or you put a negative on it. So you can play around with that. Then the second is design variables. Design variables are all the things that you can modify in your problem. That's X vector. And then you have parameters that what you're assuming to be fixed. And usually variables and parameters are sometimes interchangeable depending on what is the scope of your problem. So to limit the scope, you sometimes keep a lot of things as a parameter and you have lower number of variables, but that is depending on the problem. And then you have constraint. Constraints are the things that restricts your problems, and they are usually inequality constraints or equality constraints that you should not exceed these constraints within problem definition. So once you have defined an optimization problem, you need to solve it. So you need an algorithm for it. So one of the very common algorithms, what we kind of encounter, if you remember your calculus from high school, if you are dealing with a single variable problem, you take first differentiation, equate it to 0, and that's where you get the saddle point and different points. And if you do a second differentiation, you get to know whether it's a minima, maxima, or a saddle point. So basically the second derivative. But most of the problem what we are dealing with are often multivariables. So then in that case, you do a partial differentiation and you take gradient and Hessians of the problem. And based on that, you judge how your solution is. And that's how most of the gradient-based algorithm works. Basically relies on starting point, and then the algorithm kind of moves into different points to find that minima point. But just to give out a message out, what I want to say here is that most of these things, what we see, gradients and Hessians and algorithms, they are solved using numerical approach. So we do not solve a function, we rather let the computer program iterate our problem to reach that point. And these gradients and Hessians are most of the times are estimated using a model on the back end. So there are a lot of settings which are needed in there. So it comes back to how we define the optimization problem itself, whether I have an optimization problem of this surface or what kind of objective function I'm posing is kind of dictates a lot on what kind of solution methods are we selecting, whether it's suitable for gradient-based algorithm or not. So that understanding is needed. And if the algorithms are not suitable using gradient-based, then we move towards more non-gradient-based approach. And these are the methods where we find the optimal function without using derivatives. And most of the thing why non-gradient-based optimizations are useful is they're very good at handling discrete variables. And we also know from experience or through our knowledge that there are many local minima, or they have a disconnected feasible regions that we cannot use derivative-based methods. And if you remember, there are probably most of you would have heard of this. There are deterministic approach where you can go with a pattern search and so on, and also very famous stochastic approach, genetical evolutionary algorithm or particle swarm. And in my experience, when I started doing the research, I found, I would say almost 70% of the paper using genetic algorithm in minerals engineering. And often the motivation for that was that the problem is too complex to understand and define. And I think I remember I was reading few paper where everyone was talking about NPV, net present value function. And I tried to really decouple, like, what is this NPV function? And it's often quite complex, and most of the researchers were not very clear in writing the function definition that well. And from experience, or also from the theories of this, genetic algorithm will not always give you a global optima. It just depends on how you define the problem. So understanding of the optimization problem, what you're posing, it becomes even more influential in selecting what algorithms do you need. Sometimes you could solve things with the simplest algorithm if you know what problem you're solving. Okay, now you have solved the problem. So what are you looking for? What output are you trying to get from optimization? So many a times you are basically trying to find what is my global maxima or global minima. So you basically want to find these points in your solution space. Sometimes you are actually, you know, the global optima and maxima, and which is often not talked in mineral studies. What is the robustness and reliability of my solution within the problem definition? Because as you move, if you get a boundary solution here, what if you move a little bit out, then your problem is out of constraint activity. So since we live into world of variance, we need to think about if our solutions are robust enough or not. And sometimes we also look into, we don't want to find this maxima and minima, but rather we want to study two functions where how much do I gain or lose if we move from one operation region to another operation region. It's basically like nothing comes for free. So can we use these methods to find out if we are getting something, what are we losing and where are we losing? And if we can play around with that, then how should we operate our systems with that approach? So with this little bit of a background, I would then go to more detailed examples. So first is process simulation and equipment modeling, where I will show you how we have used calibration and validation techniques within middle aggregate or crushing plant simulation. So here we were working with the aggregate site close to Gothenburg in Kvene. It's a Skanska plant where they were doing, and this is just a representation of a tertiary crushing process where the material feed are decoupled from the stockpile, and then the crusher and coupled with two screens to produce different sorts of products. So if you think about modeling and process modeling at the center, as I mentioned in the first slide, there are data from the laboratory which comes from material. There are data which we could get it from snapshot from product, from doing a control experiment, and we can fit our model. But at the same time, we also are going to more towards digital production data we are available. And we basically, our KPIs and improvements are lying here, that what we can measure at the site. So how can we move between experimental data and move towards production data if we are able to close this loop with methods? And if we are able to close this loop with methods, then we have a possibility that we can go from production data to equipment models directly, because then we understand the system. And often for OEMs, I would say they get a challenge where they get a material and they need to give some kind of sort of process guarantee as well. So they often design their system in this region. So what we did for this site is that we tried to understand both digital system and also the belt curve physical snapshot performance. So we performed an experiment where we ran the plant for 25 minutes continuously after calibration of the crusher with one settings. And this plant was kind of very unique, where it was equipped with belt scale on all the conveyors. And we also installed some power measurement for those settings. And we collected that digital signature of the performance of the different belt scale. And at the same time, we also crashed up the process and we collected the belt cut sample, which gave us a product size distribution for these settings. So now how do we use this data back into the simulations? So first we start to do an individual crusher model fitting. So here I used a fast mechanistic model based on Evertson's model. And how I defined these optimization problems, they were unconstrained gradient based approach. So basically just with a start point and using simplest quasi-Newton method. So no very, very simple optimization approach. First, I tried to do a sequential where I tried to minimize the capacity, relative objective function, and got one variable. And then I did for the 4 test runs, the PSD error between simulation and data coupled by a weight function. So this is like 20, if I go here with the weight function, so these are each of these PSD contains 25 data points. And then within that data points, there are 4 settings, 4 runs we did. But what we see is that when we get these data from the screening lab, which usually use root 2 series, the points are not equidistant with each other. There are a lot of points on the fine region. And if I don't include this weight function, I suddenly start getting overfitting and underfitting behavior in my model fitting. So we use this weight function to redistribute the weights of each of the error signals. So what we learn from here is that optimization, as we know, it's only understand numbers. It doesn't know any logic or practicality. We need to introduce that in our problems. So this function really helped us to basically compensate the distance between the points. And alternatively, I could have written this into completely a log space function, but I think it was easier for me to introduce the weight function here, which basically normalized somewhere the weightage of these points. And we saw in the repetitive results as well that we got really good behavior for all single model giving all the different the CSS setting to the data. And what we also learned from here is that we were not using the cumulative domain for posing this problem. We were using the frequency domain of the data as we were eliminating the accumulated errors in this graph. So we got a quite good conformance, and especially we were trying to match these peaks of the setting change. And the problem really gave us good. And you see that I think below 2 millimeter, it was getting offset, but most of the coarse region were kind of very well fitted for all the settings. And here we were trying to, because since it's an aggregate operation, it was more important because 0 to 2 is the minimum product. So it was doing a very good cut there. So similar approach we applied to the modified Whiten model, and we fitted our screen model. So I will not go a little bit in detail here. So similar approach of minimizing the error functions with different settings. And once we got these models calibrated with the data, then we configured the process simulation in MATLAB Simulink, a dynamic simulation. And now at this stage, I would ideally say that if I run this plant, that should match my production data because it's similar. So then we took all the data streams because we calibrated all the models. We compared them with the production data and what our dynamic simulation was giving. We still found quite good conformance at most of the places, except some overloading and underloading was not captured that well. But at this point, I would say that now I can trust my simulation response reliably that it could be used for optimization. Now, if I want to do anything on top of it, I can trust it a little bit. So that was an application. So just want to comment a little bit on concluding this section that what could a future of this could look like. We have been doing a little more work within this, and we'll come with more methods. So if we want to move completely to production data and using that to calibrate our models, we would need dynamic simulation capabilities with control system, because that's how the data are usually consist of, and we need that because that's how the plants are built. We need to also think about renewed mechanistic and phenomenological model assumptions. So we can use our existing model into these systems, but we need to think about how we implement it if we are just going with the production data to the process modeling. We need suitable optimization methods to backfit this together. And we need also appropriate process data. Right now, it's a lot of mass flows are available, but I would still say that we do not have online material characterization data. If there is a change in that, or a PSD, a reliable product size distribution curves, that would also improve this method a lot. Then if we are working with these data from sensor, we need to also think about developing more data processing tools. We do it locally for this work, but as could be a lot to understand what is a control system response, what is coming from material variation, what is coming from equipment variation, and so on. And for future, it would probably need more automation in tools. And I guess it's more like data communication, APIs, and IT infrastructure. How do you retrieve and communicate between different platforms as well? And some things which we cannot answer through this, we can then turn also towards data analytics and machine learning models if some are not feasible. Okay, so The next bit is now if we know our simulation, we can trust it, then can we use some KPI models on top of it? So for this, we did another work with an aggregate producer in Sweden, NCC. And here this site was also quite equipped with the different mass flow datas and different power datas and everything in the cloud system. So we can retrieve it quite easily. What we worked here is that we looked into the ISO 22400 standard, which is automation systems and integration, KPIs for manufacturing operation management. And this ISO document, what we got was mostly they were written they were for production, but they were mostly written with a mindset of discrete production for automotive and aerospace industry. So we looked into this and tried to translate those standards into a continuous production process, which is aggregates and minerals processing. So, and I think I mostly did more on a plan and real time, logistical quantity, power consumption, and OE. Here it was limited to do the maintenance part, but mostly what we can simulate easily in the simulation today. And since improvements are iterative, we want to improve some parts of this in our process. So what we did is that using that ISO standard, we built a library of performance objective function, just like a model. We have a KPI models, which we can just plug in the material stream, input material, output material, and some more other things. And you can set your references, and then you can get your availability, capacity, effectiveness, and quality and OE out from the simulation. And since the control system is integrated, it will give you quite close to what KPIs would you expect out from your system. And it's also built in MATLAB Simulink environment. So we did a little bit of implementation on this aggregate side. So what we did was that we looked into the crusher, and here we did not do a physical experiment, but rather tried to calibrate or tune the crusher model to the data from the OEM. And also what we needed here was to understand what kind of control systems and readjustments in the crusher settings were happening. So we enumerated the discrete signals from the control and also how the CSS were varying during the operations. And I think both these two crushers were controlled differently. One needed a stop for readjustments, one was doing it without the stops. So you can have this into a simulation platform. So if you're going to design it for future, you can have these things within the platform. So then we were on the site, we observed the controlled data site, and then we can say our simulation model was close to the data, what we were getting from the site, if you have enumerated the control signals. And then afterwards, we could then plug in these KPI models and actually see what happens hourly basis. And here what you see on this graph here is what happened to these crushers on a day or in 8 hours, or I think it was a 10 hours operations here, how much it looks. So we got like around 50% here, but I mean, is it, maybe my reference value could be different, but is by design it is this, or is it by operation? So what we think is that here, if we are able to do this at hourly and a weekly basis, we can use these kind of approaches to also identify new process designs. And also dynamic simulation is suitable as an underlying mathematical response model for optimization. So if you want to go towards more product yield and so on, you can look into area under the curve. That's the dynamic simulation, because you have stops and on and offs of different things. So you don't, like in steady state, you're just looking for one point, but in dynamic, since you have this nature, you can track more accurately what's happening in the production. You can also use KPIs just on the data using TPM approach, total productive maintenance, which is Toyota philosophy. For example, here, you can just take the data, raw data signals and sort them. And what you want is the stable operation. And you can also identify how much is the idling time, unavailable time. It's a very quick and dirty way to understand where your plant is. And whatever improvements you do, you should be able to track it. So here you can get a quick and easy OE from your production system. So that's a very simple area under the curve in this graph, can give you the OE. and any improvement you do with understanding this complex layout, then it should be seen here in the data that you have improved. So just to conclude this segment, we use KPIs for process improvements and also for process optimization. For me, as an understanding, KPIs for process improvements is iterative process, and we use more manual factor and analysis using experiments and simulation to understand the improvement. Whereas when we say about process optimization, then it needs to involve some sort of mathematical application or algorithms towards goals and development, and some kind of automated design space exploration needs to be there. So that's where the terminology kind of differs in my head when I talk about process improvement and process optimization. And both in the end is a goal to improve production. So both should be able to track with the data. Okay, I'll go to the last bit of thing about now we have good calibrated models. We get a lot of KPIs out of it. Now, what can we do with these simulation platforms? So just given another example that consider this an aggregate site with secondary crushing and tertiary crushing process with multiple products coming out. Another site where we kind of want to get a more fines 0 to 20, and then you have 2 crushers with power consumption. So if you think about any process like this, you can optimize for throughput of individual product. The sub-process value is a cost function. You can add money to it. You can have power as a function and different things. But if you think about, there are many optimization problems which exist at any given circumstance. And if you try to combine them all, then it's kind of difficult to understand what is happening within things. So if you have a lot of many optimization problems within an aggregate, how can you handle that? So I explored a little bit of two methods. One is multidisciplinary optimization architectures and MO, multi-objective optimization. And the MDO architectures are used to coordinate and collaborate a number of optimization problems within a system. So rather than making one big problem, you make decentralized optimization problem and you let an architecture solve for it. So each problems are interpretable and are easy to grasp instead of having a global. So first I tried the multidiscipline feasible, which is actually all at once kind of an approach, where if you see here, I have a function F0, which is basically a function which defines the goals for the whole system. You can sit with your team and you define what is needed for the whole system. And then you have this another set of function, which is what is needed for each sub-process, what I want to minimize or maximize, and then a constraint. And this system optimizer will communicate to your different sub-process. It could be different simulation platforms or different sub-process within the same simulation, could be anything. And then you iteratively solve this till you get an optimizer, an optimum. In the next approach, individual discipline approach, which is I am kind of more vocal about this because this kind of decentralizes your optimization problem. So you as a group can set a goal for the whole system, and you can have a different optimization problem within your each sub-process. And here the challenge comes, since you have parallelly solving 2 optimization problems, you need to manage the variables if they are shared. How do you handle the duplicate copies of the variable? So that algorithm and architecture of this will handle that, and it will try to converge within this. So you have essentially basically made a global objective and individual sub-process objective, which is more controlled by individual section manager. And then you can see where is the good points there. And the last one is a little bit of genetic algorithms, which I showed you already. Sometimes you don't want one solution, just want to understand the flexibility of operation. So how much can you gain on one function to another? So here I think GA is kind of very effective. You just treat the whole system as a black box and you can solve for multiple functions. If you are interested in reading more about MDO architectures, there's a very nice reference paper, but I would not go into details of this. There are a lot of ways to solve it. Just to give you a little bit of a distributed architecture on collaborative optimization to give you. So there's an optimization problem at a global level, and there's an optimization problem at individual sub-process level. So an example of, maybe we have not done this, but it could be something like, what happens when you minimize the global capex and you have to maximize the global production target, and what happens to your individual local opex and local production targets. And maybe putting one extra machinery here could reduce this. The relationships between global and local systems are kind of needed or needs to be in the background to use such potentials. For our implementation here, we use this two-stage process, and we post the problem at 2 levels. And one thing which I find very interesting about when working with these things is to always visualize my functions with the variables, because it really helps me to understand if I have a convergent problem or if my solution will hit the boundary or not. So to understanding, so visualizing a function with the variables is very good, but it's kind of okay with doing 2 or 3 variables. But once you go into 10 variable state, then you need to rethink on what approach you can use. There are ways to visualize that as well. And then we solved this. This was the way we just tested if the algorithm works or not. So we tried this problem, and we got a good convergence and interior optima as well. So what is needed once you have solved these problems is that to study convergence, to check whether it's global or local, reflect on the practicality of it's a boundary optima or interior optima, whether your solution are hitting the boundaries of your limits or if it's an internal. So you need to still go back to the physical aspects here. Okay. I'll give you an example of a trade-off analysis here. And this is a current, we are working on writing a paper on this as well. It was a work done in the same project with another manufacturing of aggregates, Swerock. It's a very complicated site, and this is just a section of there where it's a tertiary and the quaternary crushers are there. And here the materials are crushed and they are stored into different bins. And there is also a possibility in this side that they recrush certain fragments based on what is needed in the production. And then they actually have 2 parallel crusher here. So the study here is about how can you operate such complicated system to meet different demands of these products, and what is kind of flexibility do you have in building such complex plant? Are the companies utilizing it? And if so, how can they make it most of changing the settings here will influence a lot of how these products are produced, not just by recrushing, but also how you operate them. So here we did a lot of surveys to calibrate our individual models. And we did belt cuts and operated our crushers at different feed conditions and different CSS settings to just map the process. And after we did that, we configured again back into the dynamic simulation platform. And here is the first cone crusher, is the second cone crusher. They're also linked with the control system and also interlocks, where if we simulate this, so how it is it's one setting with closed site setting of 24 in crusher 1 and CSS2 of 8 millimeter on the second crusher. Every time this bin fills up at 90%, it automatically starts the flow to the crusher. And if it reaches a lower level of 10%, then it stops the feed. And the PI controllers were tuned based on the conveyor length and the response time and so on. So it's kind of very tuned plant. So this is just one setting of this plant. But if you just superimpose 2 extreme conditions here, if you run both the crushers at completely open settings, we see one response. And if you run both of them at a very close setting, we see another response. And also you see that since the filling rates are different on different bins, the amount of time this crusher is running is also changing. So the width of the production time is also changing. So you can think about if you take in the total throughput of this circuit, you need to take some kind of integration of this surface. And that's what dynamic simulation really facilitate to understand this width of operation as well. And then of course, this is just 2 combination, but there could be any combinations between these 2. So in order to study a trade-off in here, we did a very simple run on plugging genetic algorithm here. So here we just wanted to study how much can you change production 1632 of the product and 58 and 25 combined together. So we get a trade-off, how much this trade-off is, if you can produce more of this or more of this. And then these are the CSS solutions on the back corresponding to each of the solution presented here. So if you take number 17 here, then it corresponds to CSS operation of 26 and 10. So opening the complete, both the crushers will give maximum of this. I mean, it's logical, but then the question is that how much can you squeeze more fines or this product if your demand is more? Then you can maybe close this completely, and then you start closing the second crusher more, and then you squeeze more out here. So what here it is that for a plant, it could be very useful to know this, where to steer based on what kind of demands they have. And also when you're actually designing a new plant, you can run these simple simulations to actually understand what flexibility are you selling your client as well. How much can the client really put different productions? So it's not a 1-point process guarantee, but rather multi-point process guarantee that this is the flexibility your plant has. 20% of production you can switch between this one or this one. And these kind of tools, methods could easily be applied also with steady state simulation as well, if you take just want to give estimates of flexibility. Okay, I will go to the last section of this presentation, which is more on the mining side. So this was an Anglo Gold Ashanti mines. We did work together with the University of Cape Town with Professor Aubrey and his team. And was quite big plant with a 3-stage crushing plant with the primary, secondary, and 2 tertiary crushers, and then a sag mill, ball mill plant, and then followed by a leaching plants here. So what was the problem posed to us was that we wanted to first, of course, find the low-hanging improvement opportunities within the process. And the mine was shifting towards more underground, and they were getting an improved grade or in the ore. So they were thinking of turning down the operation by 30%. Can they reduce the capacity by 30%? So they still get the same amount of gold out, but could really save cost here. So their option was, one of the proposed investigation feasibility study was that, can they turn off this sag mill completely and just operate with crusher and ball mill? And then that was the thing. Then can we lower the PAT or the feed size from the crushing plant? That would be more suitable for the ball mill. And then the ball mill was that what good PAT could it receive and actually produce the required optimal size for the leaching plant. So that was the investigation, and it was a quite wide investigation. So I will show you more the work from the crushing segment we did here. So we basically have a lot of toolboxes how we do these kind of investigation, right from physical investigation, like observing physical things, doing experimental survey and laboratory, again solving, like basically doing the survey of the crusher, also looking into production data to find out where the bottlenecks are or where the improvement opportunities are and quantifying them. And then of course going to the simulation, configuring and evaluating alternative concepts on how can we push this plant more. So during this journey, I will just show you some highlights from what we found is that, yeah, in this case, Professor Magnus was jumping on every machine possible, and we are trying to measure everything because process improvement just doesn't come from like one thing. You need to understand what engineering status is present at the site to get this 5%, 10% small improvements here and there will be very beneficial for the whole process. So we looked into grizzly size, which was worn out. We also looked into the screens, and we found out that almost 40% of the screen was not being utilized in the production. And we noticed that also on the screening efficiency because it was getting overloaded. The feed was offset and then with the experience, the site has blinded the screen, and they were using this on the first deck. And then because the material is falling here, you are not using also any screen open area at this first segment here. So you suddenly realize that we could see it from the wear patterns, that where the material was touched and untouched, and where was a higher wear pattern. Also, we spotted classical segregation issues also on the crusher. That's why we were noticing different performance on these two parallel crushers, and we have more coarser products here and finer on the end. So you're not able to maintain the gap size as close as you want because the pressure limits are reached. And then we did more surveys to run this plant at different settings to map these crusher performance. Afterwards, we calibrated the models in PlantSmith, which is an online steady state simulator. It was developed by a rock team. And once we have a good conformance of the reference plant, then we can go with more like a product development approach about what kind of scenarios we can employ. So in this case, it was basically the cost base. If we keep low, high, and medium cost, and what can we change in the system that could lead to production change. So we looked into different scenarios. There was almost 15 different conceptual scenarios were made. And then we started seeing, okay, what kind of PSD can we generate it for the next milling circuits. So these PSDs, we send it to the milling team, and then they did their analysis. But here for the crushing team, we looked into all the capacities at different points. And the way to interpret a lot of these changes is that we do not accept any solution, but rather first we definitely reject certain concept which definitely was reaching certain limits. So first approach is to reduce the number of concepts there. And then the milling team took this reference mill, and they have done a parallel crash stops on both SAG and ball mill to understand and model their part. And also the cyclones were modeled, and they took these data into their calibrated simulation, and they studied how can they use different PSDs, and if they are going to use these PSDs, what kind of optimization needed to be done to maintain the circulation load right and the scat production right. So it was a very wide investigation, and I mean today it was done experimentally between crushing segment and milling segments, but it through the process we learned a lot in this. So what we, just to do some reflection on it, is that we worked very systematic with this, and it was a cross-competence team. And we found that opportunities could be from anywhere, from engineering, design upgrade, operations, operational change, maintenance change, could be many things. But we also gave some specific recommendation about what is possible within this circuit, like operating if there could be closing up the gap a little bit more, and how that could be possible. And recommendation on screen feeding arrangements was, I think, one of the major recommendation. So to summarize here, to come back to the optimization capabilities, it's a multi-layered approach that we need optimization methods at different levels. And I particularly advocate for posing simple optimization problem itself that is meaningful and interpretable, that we can take some decisions, and understanding and combining this physical world with simulation world, because we can do a lot of things in simulation, but if it doesn't make sense in the reality, then it's not adding value. It needs to make impact in the physical operation. And optimization, just as a tool, for me, is a building block for digital twin transition. So the methods could be used in different ways. And in my work, I basically have used it at two levels. One is to identify and explore operational design settings, and second is to bring up the reliability of equipment and process models and production data to create validated process simulation. So the last, I would say, what is the value potential? What we can achieve with this investments on this kind of studies and doing it. So for operation, we can understand and quantify your flexibility. And I could say that it could be easily between 5 to 20% of production improvements. For a design stage, it is basically identify how much flexibility exists in a new plant design, how much changes can it adhere when you are basically checking a little bit of a robustness and flexibility of a plant. And it's also a journey which pinpoints a lot of low-hanging fruits for process improvements. You identify a lot of things which is like obviously not suitable for certain applications. Okay, with that, I would like to end and thank you.
Thank you, Kanishk. We will now have a few minutes, 5-6 minutes for questions. I don't know if you agree with me, as I said earlier, that I didn't think this was possible to actually do because of the complexity of and the nature of. Now we talk about crushing and screening plants, but Kanishk did prove that it is possible. Everyone is muted, I see. Questions are welcome.
We have a question from Professor Tavares.
Professor Tavares.
Yeah, excellent. Thanks, Magnus. Well, Kanishk, fantastic presentation there. I think quite inspiring because it definitely deals with things that we are definitely seeing as the future of making the most out of data that comes online, but also with models that have some phenological substance in it. So very good. Congratulations on a great job. My very short question is, in the first part of the presentation, you talked about basically calibrating the Everton's model for the crusher. If you could comment just a little bit on that, because actually in the beginning, the model was meant to be essentially a predictive model in the sense of having no loose parameters. But then you mentioned that you actually did fit that model. Okay, can you just quickly comment on that?
Yes, so that was not a full Everton's model, mechanistic model. It was some parts of it are translated. So we had the geometry was there on the crusher. So we just needed to fit a little bit of a geometry one parameters for the capacity function, and then we knew the material which we tested at the site was a granite, which we already had a reference point. So we rather tune the model with that parameters on the material thing. So with the physical setup, we a little bit tuned the model, did not backfitted it completely. So that's, if I could show you. Wait, let me just. We go back to the slide here. Yeah, so here, these, if you see that it's an unconstrained gradient-based approach. So we started with 111, and we had the material property on the back end. So we just let the optimizer, basically here we were only fitting the material breakage basically with this model. Rest everything was parameter was fixed because we knew what exact crusher model we have tested and so on. So we had those things in there. So the only these variables were basically the functions defined to create material parameter, and we tuned it. So it was not something, we did not find the material by itself. So, but
Okay.
it was very efficient. If you know a lot of reference models with the material, then it's basically in the processing, you are just trying to maybe tune it. Then of course I could go one step back and actually do a laboratory test and cross verify whether my tuning was okay or not. But I would rather go towards production if my tuning is suiting my production operations or not.
Okay, thanks.
And the flow models were not included in this. They were also considered, and there were a lot of assumptions, and that's why it's called fast mechanistic model. Thank you.
Just a question from my side to you, Kanishk. just to repeat what you have already said, I mean, this is obviously a massive piece of work, or there are so many potential alternatives. But if you would just summarize this in a few bullets, how would you proceed if you see a plant for the first time? What would you do in steps?
If I see a plant in the first step, I would first go to the data, historical data. That would be the first, with the layouts and so on, because that pinpoints a lot of improvements where we need to focus on, and the physical observations of the plant. And then if we are going towards a more modeling based approach, then I would say that if we have a good backfitting models, we can do either surveys or look into these production data and actually tune our models quite well. And for that, of course, the underlying assumption is that we need to have a dynamic simulation capabilities to fit that. And then it's more about discussion with the plant about what they want to achieve with the process improvements and optimization.
Thank you. Are there more questions?
I cannot hear you, Malcolm.
Just checking if you can hear me. It's not
Yes.
clear.
Yeah, we can.
No, now we can hear you.
Two devices were muted by mistake. The parameterization, can you do that on dynamic data rather than needing a steady state period?
Yes, it would be possible if we have a tuned control systems in our dynamic simulation. And that's which basically goes back to steps of things we need to do. And the question, when I was working on this, it was like, do I first tune my control system in the simulation to get the right response, or what should I tune first? So I think it would be a sequential steps we need to follow to get that information in the dynamic platform.
So you understand, right? You're saying you'd look for specific step changes in performance for tuning
Yes.
the parameter.
Yeah, and what I have been doing and a little bit working on is that like in the data machine learning models, you kind of want to get this from the historical data. But my approach is a little bit here is like, can we run the plant manually at multiple states by experiments? Maybe it will take like an hour or half an hour, I don't know. Maybe I'm more talking about from a crushing circuit point of view. And then we record those online data about the response behavior, and then use that to calibrate the models instead of relying on a historical data with uncontrolled parameters. So we create a digital signature of the process performance.
Yeah, I've always seen that as the problem with trying to parentize models on just production data is the multivariation taking place, interference from the control system,
Yes.
unknown changes. And
Yeah.
so people have this dream, you just throw the data at the model, operating data, and it parametrizes it. I've never seen that dream even vaguely come to fruition, which is why I was asking you. So maybe it can be used to online tweak the parameters, but I don't think to set it up is my experience. So.
Yeah, with the convolution conference, we did another more extensive work than this, was with the 2 variables in the crusher, and we have basically data for the whole, like a mapping of the whole production levels. And then we are trying to use that to backfit models and see if we can reach that state. And that's when one of my thing is that we need to have in some sort of data processing tools, we need to a little bit do an investment on how do we get that, what you just said, between basically here, how we get this different data control response, material variations, and so on, if we are going completely digital systems. So we need some sort of intelligence in there as well.
You do, and I just notice I do more the milling than the crushing side, but people are trying to parameterize models and they're missing the most important input data. And then you just know their models got to be at the best suspect. So a conditional change in the model will be completely wrong because it's misparameterized. So that's, I think, is the warning of knowing you are actually gathering the data required for the parameterization.
And another thing, Malcolm, which I also think is this renewed mechanistic and phenomenological model limitations. So all these model parameters, how much can, because now I'm doing unconstrained approach, but if I go towards a constrained optimization approach, then I will limit them that these variables can have upper and lower bounds between these, because that's what practically says from the experiments or from the known model behavior.
That was actually my other question you've just answered. So the constraints on physical parameters is important. So
yes.
I really like your mechanistic style approach, because each parameter has a physical significance. You only have a physical range. And I think it's missed in online dynamic modeling, that importance, that it's not just some fictitious parameter. No. It has some meaning. That's very good. Thanks a lot, Kanishk.
Okay, everyone, we are a few minutes past the hour, so I think we can close this seminar for today. Thank you again, Kanishk, for a very interesting presentation. Thank you, everyone, for joining.
Yeah.
Any closing words from you? Yes.
Yeah. So thank you all, and I think
thank you.
Next month I have another GCC seminar. Thank you.
Bye, everyone.
Bye.
Thank you very much for an interesting presentation.